Hi, everybody. Welcome to this session with Dr. Erin Boyle, who is head of data science at Myst AI. She has been working in AI for quite a long time, previously at Stitch Fix, and before that she had completed a PhD in physical chemistry. So very impressive background. And today Erin will talk to us about the work that Myst AI does on forecasting electricity demand. Fundamentally, Myst is building a time series forecasting platform, and they're focusing on climate relevant use cases, of which forecasting electricity demand is one of the most important and most challenging ones. Go ahead, Erin. Please share your screen and begin.
All right, thanks, Eugene. All right, can everyone see this okay?
I can see it.
Thanks. All right, so as Eugene said, my name is Erin Boyle. I'm the head of data science at Myst AI, and I'm going to be telling you about how to build accurate electricity demand forecasts. As an outline for the talk, I'll start with some introductions. Who is Myst AI? Then I want to tell you a little bit about the electricity demand problem itself. At that point, I'll give you an overview of the basic ingredients of a forecasting solution. And then at the end, we'll get into some of the more fun kind of real world complexities that come up. So perhaps I'll start with myself. Actually, Eugene gave a really kind introduction already, but as a little bit more background, I came to the energy sector via a somewhat circuitous route, like I think some of the other speakers we've heard from, maybe more yesterday than today. Like many people coming to data science about a decade ago, I came out of the physical sciences where I was actually working on some kind of foundational spectroscopy work that had the intent of improving our ability to understand solar water splitting. Came out of that experience certain that I wanted to do more directly applied work. And as Eugene mentioned, went to Stitch Fix, where I ended up building out the company's core style recommender system. And over the course of years, kind of building those recommendations into essentially all of the kind of services and products offered by the company. In 2020, became quite eager to rejoin the climate community. And so I joined Myst AI, where I've been the head of data science for over 1.5 years, managing this delightful team of 4 people shown below, and offering forecasts to the clean energy sector at large. So who is Myst AI? No, we are not the 90s computer game, though we do have an internal package called Atris. What Myst does is we offer forecasts to the clean power sector, and we do this 2 main ways. So I'm actually going to start with the box on the right here. So we offer a forecasting service or solutions, and we've been doing this for our entire lifetime of over 3 years. And with this service, we offer end-to-end forecasting workflows that are built and maintained in-house, where customers simply subscribe to some kind of simple API integration. In the last 6 months, we have also been offering the Myst platform. So basically, we've taken everything we've learned from the forecasting solutions, and our intent is to kind of scale up our impact by making it really easy for a wide variety of users to leverage all of the kind of ingredients we know are important to building forecasts, to autonomously build and deploy their own forecasts, taking advantage of whatever kind of expertise they may have in-house for their particular problem. So why forecasting? I think there's probably a pretty wide range of expertise of folks on the line. We just heard from a bunch of experts in the energy panel that certainly doesn't need to hear about this, but for anyone without this context, forecasts are actually essentially everywhere in clean energy, actually in the energy sector broadly. So I'm highlighting here a handful of customer types or domains that we offer forecasts to or expect to in the future. And maybe I'll just highlight a couple of them. So one type of company that we've been working with quite a bit in the last 6 months, but is not the focus of today's talk, is battery storage operators. So Myst is very excited about this application because, as many of you know, batteries are undergoing exponential growth in the grid right now, and they're a really key ingredient to helping take our intermittent solar and wind generation and spreading it out across the day to increase the penetration of renewables. But what do battery storage operators need to do? They need to be profitable. And to be profitable, they actually need to define an optimal dispatch schedule based upon an understanding of what wholesale electricity prices are going to be in the coming hours and days, or day, basically. So there are a wide array of price signals that we help these types of operators forecast. A type of customer that's much more relevant to today's talk is load serving entities. So for anyone dialing in from the Bay Area, this could be, for example, a community choice aggregator like East Bay Community Energy. It could also be, some kind of utility, muni, co-op. And essentially what these entities need to do is they need to anticipate the power requirements of their service territory ahead of time so that they can go buy it. They're often going to be buying it in the day ahead market if they're in an ISO or an RTO, or they may be interested in actually also getting electricity price forecasts and making decisions about whether to procure power from the day ahead market or the real-time market. Another example is renewable power providers. So, solar and wind farms, they need a variety of different forecasts, including generation forecasts. We've worked with some in Europe that need market imbalance. Then we have distributed energy resources, district heating suppliers, demand response, EVs. Grid operators themselves rely upon forecasts to actually run the market. They need load and generation forecasts in order to even set prices. All right, so Myst is really interested in providing a platform that makes it easy to solve this wide array of use cases. So this is just a brief overview of the platform. I won't be able to fully do it justice before diving into the talk, but in general, what we are offering is a fully managed, time series focused MLOps platform. So again, our intent here is to make it very easy for users to build highly accurate and reliable forecasts. And the philosophy guiding this is that we want to basically serve as a wrapper that democratizes access to all the kind of best open source tooling out there. I would say two of the important differentiators between us and other MLOps platforms are A, our time series focus, and B, our integration of third-party data that is relevant to electricity. So on the time series side, what I'm showing on the left here is a forecasting workflow, a DAG or a graph. And what's kind of different between this and a DAG you might see from something like Airflow is that at Myst, we have a time series data model that is powering our workflow orchestration, such that within our framework, users or data scientists are kind of stringing together data sources, operations, and models. And time series are the objects that are flowing between all of these. And because of this somewhat more opinionated framework, we can actually not just orchestrate the tasks that you're running, but actually the data as well. So users only need to kind of define the logic of their forecasting solution, what types of transformations and models they want to be using, and all of the kind of like storage of the data, all observability is completely deterministic based upon what that graph looks like, and the user doesn't need to worry about it. On the data sources side, so I think this was mentioned in the panel just before this, but really in forecasting, everything comes down to the data. Are you making forecasts using the right inputs? So some third-party providers I'm going to highlight here are the weather company. So this is an IBM subsidiary that provides highly accurate weather forecasts of various types at pretty high geographic granularity as well. And we also integrate with a provider called Yes Energy, which has a really rich set of market data, anything from, wholesale electricity prices, load, and actually they themselves also integrate with a large number of other third parties as well. Users working with our platform will use one of two interfaces, or really both of them. So we have a web application and a Python client library. Data scientists will probably do most of their work in the latter, but the web application offers kind of visualization and monitoring. And you'll see some screenshots from it throughout this talk, because I think it's a nice visual way to kind of understand some of the concepts that I'll mention. Beyond that, in purple are some of the functionalities that the platform either has or will be rolling out quite shortly. We're actually in alpha right now. So backtesting, hyperparameter optimization, deployment, versioning. And if you're to go another couple of quarters out, we intend to offer things like domain-specific AutoML for domains like, for example, demand forecasting. So it's been a pretty fun ride. We partner with actually a bunch of leading energy companies. We're proud to serve the 3 largest power companies in the world. This is just a small subset of our customers, but ones we're really excited to work with. And we are continuing to grow and be excited to serve the industry even further. All right, so electricity demand. Let me just show you quickly what this data looks like to help give you an understanding of what goes into forecasting. So I'm just going to give a really simple example to ground anyone unfamiliar of CAISO. This is the California ISO's system-wide demand. So this is a really nice kind of predictable signal that I think helps highlight some kind of obvious behaviors of demand time series. A small note on semantics here. You'll notice this is actually titled load. I'm going to kind of use those terms interchangeably. They're not actually literally the same thing. So demand has units of power, megawatts, load has units of energy, megawatt hours. But because in many cases this is reported on an hourly level, we have a tendency to kind of swap them. So within this time series, I think you can see one clear thing. So within California, like many places, load is seasonal. In California, it peaks more in the summer where folks are turning on their ACs a lot. Another fun thing you can see in this data, if you squint, is that actually there's just ever so slightly a trend downward over the last 8 years. So this is actually a result of energy efficiency. So California is not increasing its demand over time. It's going down ever so slightly. Demand tends to have very strong weekly periodicity as well. You can see that we consume more energy on weekdays than on weekends. And finally, also, there's a strong daily trend. So you tend to get a bit of a peak in the morning, a lull in the afternoon, and then a stronger peak in the evening when everyone kind of comes home and turns on all their electronics. And electricity demand is very much related to, I'm showing temperature here, but weather broadly. So there was a heat wave in July 2021, and demand went up with that heat wave. In general, weather is quite predictive. Okay, so you might have seen all those time series and thought, boy, that's a pretty easy problem, and probably it would be. What does a more realistic demand project look like? The signals are actually going to be a little bit messier than that. So often we're serving, regional or local service territories. So this top left is an example from a load serving entity in California. And in the bottom right, I'm showing, actually in this case, it's heating demand, but heating and electricity demand have very similar behaviors to one another. So this is an example of a much more noisy signal of heating demand in Scandinavia. But at the end of the day, the same principles apply. The last thing I will mention is that data availability is an interesting factor in the real world. So I wonder if anyone could work this kind of thing into a Kaggle competition, but it turns out to actually measure power consumption, you need to use meters. And these are imperfect devices that need to all be aggregated to understand exactly what happened in the past. And so there's actually a data gap between the flow date, which is, when the power was actually consumed, and when you first have an estimate of what happened in the past. So across a number of customers we've worked with across the country, we've seen that it tends to take something like 2 to 5 days for some kind of initial estimate to come in of what happened in the past. And this is called a settlement because of the kind of settlement process of billing essentially with the market. And then often there's about a 2-month delay until you have a final settlement. A final source of truth of the actual power that was consumed in the past. Okay, so let me show you some basic ingredients of a forecasting solution. And you should always start with data, because in machine learning, that's the most important thing. So it will come as no surprise, I think, given some of the behavior you saw in the graphs I just showed you, that time features are going to be an important component of a model here. Folks literally use more power at night, for example. So I'm showing a screenshot of our web UI. In reality, users using our platform would probably be building this with the Python client library, but you can also do it in our web UI. But here you can see kind of a dropdown of some time fields that you can just plug into your workflow in the Myst platform. So, day of week, day of year are kind of clearly the types of features you'll want to be choosing. I would recommend also creating cyclical versions of those same features to do things like smooth out the boundary between December and January. And you can do that with numerical expressions or just with NumPy if you're doing this at home. The next piece is weather features. So again, I'm showing some examples of some fields that you can just plug in if you're using the Myst platform. And here, I think you get a little bit more of a benefit from the platform, while those time features you can just get from pandas. There's actually quite a bit that goes into plugging good weather data into your model. So, you're going to need to set up a contract with a vendor. You're going to need to integrate with their API. You're going to need to, deal with their rate limits, etc. Myst is really interested in making this process as easy and painless as possible for as many people as possible. There's some interesting details under the hood here that I want to highlight. So in general, these weather providers have a large number of APIs actually for slightly different signals. And so even just for one field, temperature, at just one, what's called MEDAR station, you can actually use different APIs to get different time ranges of data. So just like in the load settlement process, for weather, you also don't know exactly what happened in the past for something like 24 hours. So for any kind of temperature observations more than 24 hours in the past, you're going to be hitting this cleaned observations API. If you want data from the last 24 hours, that's a different, basically pre-cleaned API. And then if you want data for the future, forecast data, you're going to be hitting their forecast API. So Myst has made each of these data sources available separately from one another in what we call source connectors that can be independently referenced within your graph. But a kind of 95% solution for how to deal with these 3 different time series is to do what we call layering, to basically stitch these together into one time series where you, what I'm showing on the right here is the prioritization of these, what we call layers. So basically you can think of these as fallbacks where a time series is going to be constructed based upon some prioritization of upstream fallbacks, upstream time series, where whenever the highest priority one isn't available, you're going to fall back on the next one. So this prioritization here is saying that if there are cleaned temperature observations available, please use those. Fall back on recent if they're not available, and fall back on forecast if that's not available. And that's going to create basically one time series, one column of your data frame. If you go with this approach, what you'll be doing is training on what we call weather actuals and making predictions using weather forecasts. Again, not the only thing you can do, but something that we see people doing quite often. And so we make it available in what we call a recipe. Something that is quite common in this field is to use a large number of transformations on your input features in order to basically help the model more quickly learn different types of trends. So that might be rolling averages, differences, lags. You'll often see quite a bit of these in an optimized forecasting solution. And then finally, demand data itself. So for many of our customers, actually, they're forecasting proprietary demand data that they're actually going to be inserting into our platform. This is something else we support. But in some cases, folks actually want to forecast publicly available data associated with a load zone. And for this, you can turn to Yes Energy. And so just to kind of highlight how rich the data is, like this is just load signals and just in the California ISO. And you can see there's maybe 24 or so load zones that you could independently access. So I'm actually going to spend probably the least amount of time talking about models. Again, I would say that our kind of philosophy here is to democratize access to winning open source models. So if you look at, for example, the Kaggle M5 forecasting competitions, which is a slightly different application, but still relevant, what you will see is that overwhelmingly gradient boosted decision trees do really well in the forecasting domain. So you can see that we offer a connector to both LightGBM and XGBoost. In the energy panel prior to this, the concept of probabilistic forecasting was raised, and I think it was Martina who mentioned like you can't actually anticipate every kind of outage that might happen, and I think that's true. And what we see is that actually a lot of our customers are interested in forecasting prediction intervals, and that's something that LightGBM specifically offers, is more flexible objective functions. You will also see RNNs like LSTMs being leveraged successfully in these domains, at least for shorter horizons and for situations where there's not a big data gap. I wouldn't necessarily recommend it in the demand use case. So in this case, we're providing a wrapper to the PyTorch forecasting implementation of the RNN with just some very small changes. And you'll also see kind of simple models like multi-layer perceptrons being competitive in some cases. And we plan to kind of add to this library over time. You can see that we also have some kind of benchmark models that you can use to compare and understand how much lift you're getting over a less complex solution. The other tip I would give is to leverage ensembles. So electricity is a bit energy poor. I'm sorry, data poor. It's pretty common for you to have something like hourly data going back 3 or 5 years. That's actually not a lot of observations. And actually, I think that's a reason why you see gradient boosted decision trees being quite competitive, is that, it's harder for like a really complex neural network to really have the data it needs to feed it. But you can eke out some accuracy improvements by ensembling across different approaches. So again, the Myst platform makes this pretty easy. You can just stick a handful of different model nodes into your DAG and combine them into one ensemble at the end in actually a few different ways. So the validation process in forecasting, I think, is an important bit to pay attention to. So for anyone familiar with this, you don't want to do the kind of cross-validation you do in other machine learning sectors where you do kind of randomized train test splits. In forecasting, it's really important that you are always splitting chronologically. And so in general, this kind of cross-validation is called walk forward or rolling origin cross-validation. And the general idea is that you kind of want to do splits by going back in time, training on the data that was available up until some point in time in the past that we call the reference time at Myst, and then making predictions for a period of time after that, and then kind of walking forward and repeating the process and kind of stitching those predictions together in order to get some holdout metrics. The philosophy that we encourage at Myst, though, is to really think hard about how to make that walk forward cross-validation really mirror production. And so because of this, we have actually made it possible to parameterize your backtests with exactly the kinds of parameters that you would use when you go live in production. So what are you going to do when you go live in production with some forecasting workflow? You're going to define a schedule on which your models fit. And you're going to define a schedule on which you make predictions. For that fitting process, you're going to define what range of data you fit on in the past. And then for that prediction piece, you're going to define the horizons that you're forecasting. So it might be the next week. It might be that you are interacting with day ahead markets, and at 7 a.m. each day, you're forecasting midnight to midnight of the next day. That might be the set of horizons that you care about. So it's important to be able to parameterize your backtests with all those same parameters in order to get metrics that are really one-to-one with what you'll see in production. Once you have the ability to assess metrics with a backtest like that, you can move on to tuning. So here, I would recommend leveraging Bayesian hyperparameter optimization. This is a feature that will be coming on our platform very shortly. So we're starting out by offering an integration with HyperOpt, where you can use the tree of Parzen estimators algorithm to more efficiently search your space of hyperparameters and converge upon a set of hyperparameters that maximize your objective function. So this user experience will look much like parameterizing a backtest, except that you can also define the search space that you'd like to search over for your hyperparameters. And I would say that in our experience, this is actually pretty important to do, especially if you're working with gradient boosted decision trees, as they do have a large number of hyperparameters that interact with one another and with your data. As far as deployment, I'm pretty sure this is going to be quite obvious to everyone on the line here, because this is a conference of technologists. But continual retraining is actually something that we have found is a little bit daunting to much of the energy sector. So there's a range of companies we work with, and some of them have very sophisticated machine learning expertise and infrastructure. But there are a large number of like awesome companies in clean energy that really don't have the bandwidth and expertise to set up a deployed machine learning workflow that does continual retraining. And so I do want to emphasize this is an important part of achieving accuracy. And with the backtesting parameters that we offer, it's quite easy for you to determine on what cadence you need to retrain your models in order to avoid model drift and maintain high accuracy. Another best practice I'll kind of shout out is to always define a fallback. And I think this is pretty important in this sector, especially. So even the best third-party providers just don't have 100% uptime. And so it is important to be prepared for there to be some kind of outage in your input data and to have smart fallbacks. So Myst actually offers this via the same feature that I showed earlier in the case of weather inputs, where you can use this kind of layering functionality of our time series to fall back per timestamp in your forecast on some simpler model that has fewer upstream dependencies. So in this case, I might have some very complex load model, has a lot of features going into it, but it might fall back on, say, a 2-day lagged persistence model. All right, so I think none of what I just showed is rocket science, but hopefully you come away from it with some understanding of how it would be pretty easy to plug all those ingredients together on the Myst platform, though of course you could also do them in-house with whatever tooling you use. I'd like to now introduce just a bit of real-world complexity, so return to that data availability complexity that I mentioned earlier. Because I think that this highlights one kind of fun element of forecasting. So, as I mentioned, if you're forecasting demand and you're integrating with real data, you're going to get this proxy data that comes in 2 to 5 days after flow, and you're going to get this final data that comes in about 2 months after flow. We have seen the data be structured slightly different ways than this as well, but this is a pretty common one. So if you're a data scientist forecasting that final settlement, what are your options? What might you try? Well, you might try directly forecasting final settlement with a multi-month data gap. Experience tells us you don't want to do this. Retraining more often than that on more recent data and using things like recent lags of your target are pretty important to getting high accuracy. So this is not really going to cut it as a solution. You could directly forecast the so-called proxy settlement with a small data gap. This, in our experience, we have seen this work okay. Basically, this just depends on how simple the proxy and final are to each other. But often they're not that simple. And in that case, again, your accuracy is really going to suffer. Two other ideas I'll put forward are, well, you could kind of splice the two together, which I'll talk about more on the next slide. Or you could even create kind of stacked or chained modeling architectures where you're say forecasting the proxy and then mapping to the final. So to dig into how you would do this, what do I mean by spliced? I mean basically using the final settlement wherever it's available and then kind of splicing on the proxy for the missing region. What does this look like? This is this layering thing again. This is why we made this part of our kind of core data model, is because this functionality comes up so often. So you can layer together the initial and final settlement in order to just use that as a target and create a forecast. Okay. The other approach, and I realize the word stacking is used a couple ways out in the industry, but I think this is about the closest we can get to the right term. So in this case, what I'm saying is that you can create a graph where you forecast the proxy because it's got that small data gap. You can take into account recent trends. And then you just figure out how to map that to the final. Maybe you do some kind of transformation, maybe you learn a residual, whatever it is, and then basically adjust, and then that's your final settlement forecast. All right, so that's all well and good, but how do you actually decide which of these various approaches is going to be most accurate? So I think the tricky part of this is backtesting to compare these different approaches to each other. And I think this highlights, again, a kind of fun part of forecasting. So remember that backtests should mirror production. But unfortunately, in production, the target data that we're training on in these more complex approaches, so I'm highlighting the kind of spliced approach here, that target data isn't just filtered at each historical reference time, its actual values differ. So if you look at the point in time right before reference time 0 here, if we are training at reference time 0, the 2 months prior to that is going to be proxy. But if we're training at reference time 1, then the 2 months prior to reference time 0 are going to be from the final settlement. So this is just higher dimensional data. And the way to really reproduce what's going to happen in production in a backtest is to pull the time series values as of the time that they were stored. So this is one of a large number of reasons that our time series data model also built in as of time as a kind of core component. So for any time series, you can record both what the values of that time series were at real points in time, what we call natural times, and you can record what we thought those values were at different as of times. So I imagine many of you work in data science or ML teams that use as of time. But for anyone who doesn't, this is a way to kind of think of like snapshotting the past. I apologize, in this particular picture, I'm actually showing an example for weather, not for demand, but it would look essentially like this. So as of time moves forward, as you go up in this chart, more and more of the final settlement, that would be the black values, are kind of solidifying. And then the red values here would be the proxy that's being used until the final becomes available. And then the unfilled spaces would actually be the time periods you're forecasting. So if you store data in this way and make it accessible to your backtests, that actually enables experiments that, again, like can truly replicate what will happen in production. And this is something that we have used internally and really benefited from for exactly this situation of demand forecasting in order to decide which of these different approaches is best. And I should say it's not a feature that is externally available to our users yet. We will be working on it in Q3. And I'll just highlight quickly, so this is stepping a bit away from the demand forecasting focus, but this kind of improvement to backtesting is actually something that has a lot of other ramifications as well. So I'll just highlight one other before closing, which is that in the electricity space, there are forecasts everywhere. So there are temperature forecasts that feed into models that do load forecasting. And there are load forecasts that feed into models that do price forecasting. And so it turns out that if you have forecast inputs into your models, you're hitting this exact same kind of issue that I described with the demand data that's coming in over time, where you want to kind of have a time machine that accesses data by as of time in order to accurately assess the performance of your model in a real world setting. Okay, and I think that's it. So I think I'm pretty close on time here. So I'll just quickly say, like, forecasts are everywhere in clean energy. Accuracy relies upon many factors, but I will especially call out getting the right data and doing the work to do those data integrations in a robust way. And then pursuing the right validation process. And then finally, that modeling the real world complexities is hard. And I think this is where you really start to get the benefits of a platform that does things like backtesting in a way that's integrated with the data itself, that you won't be able to get from the kind of off the shelf forecasting tools out there, and benefit from things like layering and this as of aware data model.
Yeah,
and
thank
that's
you
it.
so much. Sorry, go ahead.
I'm happy to take any questions.
Yeah, thank you, Erin. Again, dear audience, please add more questions. I have a couple of my own, but while I'm asking them, please think of yours as well. Yeah, Erin, one thing that comes to my mind is you're sharing this platform. Is it possible for people who want to get into ML and energy space to play around with it as individuals, or is it for enterprise customers only?
Yeah, it's a great question. So right now we do provide access to the platform somewhat selectively. And it's not that we intend to always only serve enterprise customers, but we do provide selective access for right now while we're in alpha. We are looking forward to a future where folks can trial it more seamlessly. But for right now, if you're interested, you can go to docs.myst.ai to just read about it. And you're welcome to send us an email at hello@myst.ai and express your interest, and we can see what we can do.
Wonderful. Yeah, I imagine many people would love to play around with it. Yeah, one more thing I want to ask is, can you tell the audience like what kind of people are on the team? Like, I know that Peter, one of the founders, is an ex-Googler. I know that Emily, your head of engineering, is also from that. Like, what's the rest of the team like?
Yeah, that's right. So our other co-founder, Tishan Palazzi, he came out of Rocky Mountain Institute. And so I actually think this is a really important component of our success, is that Titian is someone that has really deep energy expertise and really understands what the sector needs, and so helps guide the product that we build to make sure it's going to be as impactful as possible. Yeah, and then on the data science team, I mean, brilliant folks. Some have had more experience within the intersection of energy and data science themselves. So one person came out of a Google X team working within electricity. Another actually helped co-found a startup in electricity. And yeah, I really resonated with some of the things that were said on the energy panel earlier, and that like you really want to try and build more expertise on the actual applications you're working on into your team. And that's something we'll continue doing.
Awesome. Thank you, Erin. And who are you hiring?
We don't have any open roles right now, but we do have a number of them kind of in the queue that we'll hopefully be posting in a month or two. And I do expect us to be looking for, I think we'll have 2 kind of engineering roles opening up before all too long. We are talking about our first product UX hire. I expect us on the business side to be looking for another business development manager, and this would be someone that has experience with electricity markets and marketing as well.
Got it. And is Myst exclusively focused on energy, or are there other applications relevant to climate for time series forecasting that you might pursue?
Yeah, it's a great question, and one that we ask ourselves a lot. I think there's nothing in the platform that would prevent it from being used in other sectors. And certainly we've thought about expanding into, say, like food waste, which is an important component of climate. But thus far, I think we've been really happy with how much traction we've gotten in electricity. And it seems like this is a sector that we have expertise on. We have some of the third-party data integrations that really help get accurate forecasts. And I think for right now, we're staying focused on that sector because we think there's so much more growth we can do just within it.
Got it. That makes sense. So Troy Hodges is asking, are there any trends in energy use or production or weather that you find make forecasting more difficult at the geographic scales you're looking at, such as larger EV adoption or climate trends?
It's a really good question. I mean, in general, there are going to be so many things changing under the hood with systems like this all the time that I think that's a huge part of why you want to continually retrain your models and enable your models to be like reactive to, it would just be very hard to pipe in every bit of information that is impacting electricity demand over all of California or something like that. But yeah, I mean, certainly like I can think of things like they might be more kind of like structural changes in power markets. So for example, we do a fair amount of price forecasting at Myst, and like ERCOT, for example, changed how their so-called price adders worked at the beginning of this year that changed what real-time price spikes, the behavior of real-time price spikes in ERCOT in a way that is highly impactful to battery revenue. And so I would say things like that are things that we definitely try to keep an eye on, make sure the data is available to customers. We try to understand how to forecast it ourselves, and we try to give people the tools to do the experiments they need to do with their expertise to build in whatever behavior into the model is going to help it deal with that change.
Got it. Yeah, thank you for explaining. And last question from Gabriel at Fluence Energy. Have you found any pitfalls around continuously retraining? For example, is there a retraining frequency you found to be too frequent?
Interesting question. No, I don't think that we've seen a too frequent training. I mean, I just like at some point it's going to be more computational cost with like little benefit. But if you're thinking of something I'm not, shoot me a note later, Gabriel. I'm curious what you have in mind.
Got it. All right. Yeah, thank you so much, Erin. We need to wrap up this session, but this is great. I personally always love hearing about platforms that are applicable to a lot of things at the same time. Hopefully the audience enjoyed this too. Thank you. See you all in the following sessions.